Hello everyone and welcome to Make Your Roguelike in Haskell, part 3. In this video series we're trying to learn Haskell by making a small roguelike. So I recorded a version of this video yesterday where I've done all the code and I planned to upload it, but by the time I went through video I realized that my CPU usage was over the top and my video had numerous graphical glitches as the encoder was not able to keep up, and unfortunately I already put the code online. So this video is gonna be a bit different because instead of coding I'm just gonna run through whatever I already had done yesterday. Okay, so I'm just gonna run some music and we can start. So first of all, correcting errors from part 2, and there were few. Our applicative instance for the entity class. As you can see, both applicative and monad instances are gone. The reason for that is because I wanted to not add the code until I actually need that code. The problem with applicative instance was that it looked like this. This is good. Now, I assumed that this is a good instance. However, this violates the interchange law, so it's wrong. Fortunately, thanks to the fact that vector2d implements instances the applicative itself, we can do this. And this is a correct implementation that satisfies all the laws. However, I'm not interested in having it simply because I don't see the need for it. So that was the first thing. The second thing, our game now added type variables instead of having concrete types in here. And the reason why we've done this is because it's multifold. First of all, we want to be able to write code where in the declaration of the code, right here, we specify what do we care about or what do we don't care about. Now, what do I mean by that? If you remember, our game used to look like this. The tilemap, just ignore for now, because the tilemap used to look like this and it used to be an empty data right here like this. But we actually implemented a tilemap, so let's just leave it for now the way it is. Alright? So if we would put the data, if we would write a function that uses a data such as this, in, for example, implementation of the move event, we are completely free to do absolutely whatever we want with any of the data types, any of the concrete data types inside our class. This means that we expand the amount of correct solutions, as seen from the perspective of the compiler, as the implementation of this function. And this means that we rely only on the identifier name, which says update and then the parameter move. We rely only on this to assume that this implementation is actually going to update the position of a character, right? So I like, and I think everybody should strive towards this, I like encoding this data into types if anyhow possible. And one way of doing this is through polymorphism. See, for a very long time, I thought that polymorphic code is a code that tries to cater to the user, you know, to the client of this certain function. So you try to make polymorphic code in order to help them use your code in a variety of different situations. But only recently I learned one very important fact that completely changed how I look the polymorphic code, and it's this. Look at the move avatar declaration. So we use our new type of game, which instead of having concrete types, it uses 4 type variables for our entity, items, enemies, and the types of tiles in the tile map. When I write move avatar, and this is how I wrote it, except there's even a better way, but so I explicitly state that I need a game with a concrete implementation of a character, and I don't care what the items, enemies, or tile map tiles are. This communicates a lot. And why? Because if I don't know anything about these types, these 3 types, it means I can't really do anything with them inside my implementation, right? Like in move avatar, I have the ability to change the character somehow, the player avatar, and I have ability to change the lists because I see the list, and I have the ability to change the entities. I can obviously change something in a tile map, and I can change the running flag, but I can't change anything that these 3 types would instantiate. This means that the amount of these correct solutions that would be implementations of this function narrows down. And aside just communicating what this function does much better through its declaration, you kind of save yourself from accidentally creating these kinds of bugs. Because these 3 types, the objects or the data of these types, you can't do absolutely nothing except just copy them back to the output. And that's it. This is why this was one big revelation for me when it comes to polymorphic code and using type constraints rather than using concrete types everywhere. You make it harder for yourself to write buggy code, and you make it easier for everybody else to reason about what your code does. And I'm going to show you an example later in the tile map code. For now, one mistake that I've done is that if you look closely here, we are actually not using anything from our character. And that's logical because our character has absolutely nothing. It's just an empty constructor, an empty value. But this function works. Why? Because the only thing we're using is the position from the entity, and entities here are concrete types. And that's okay, because we want the game to be a data type that deals with positions of different things in the world, but not necessarily interactions between these things, okay? So here, to move avatar, we don't necessarily need to know what the avatar is. We can just ignore the concrete implementations of any of these types, right? Oops, sorry, wrong key there. BCD. The reason why we put concrete types over here, as you can see there, character, item, character, it's very simple. This is an overarching update function. You know, it's likely that this function is going to touch absolutely any part of this game and maybe handle some character interactions towards each other. Probably the best thing to do would be to make update function and receive other functions that are going to handle the interactions. But for now, let's just leave it like this, and of course we're going to change it in the future. So these are the two I think very important things that we changed in our main. The next thing, we extracted the render little sub function from this where clause over here, and we put it over here. As you can see, we just refactored the code a bit, creating a monadic bind without using the do, and we created our render action. Our render action is of the curses update type. So what we do, we clear, we draw a map, and then we draw character somewhere. Draw a map uses our new tile map, which I'm going to show in a second, and the draw character is just our old function that drew the character as it did before. Okay, so draw map, it takes the map data, which is just a vector of whatever. Right now we specialize it to character. it converts the vector of this data into a list and then zips it with an infinite list that starts from 0, and then it just draws a tile. We use a function called linear to chord from inside the tilemap module, which takes the width and the index coming from right this list, to calculate out the 2D position of this current tile, and then it just moves the cursor and draws it there. So it's fairly simple. Tilemap. We've created a data type that contains name, and it contained width as word and height as word. And then we created a vector that's going to contain the data of absolutely any type. The reason why is because we want tilemap to be a data that's just going to handle the grid of any types of objects. And this means that this type variable, not only is going to allow the clients of this module to create whatever tile types they want, it's going to also make sure that we cannot write code that's going to interact directly with this data and change this tile somehow. So we loaded it from the file. I actually drew a test map right here. We loaded it from the map, and we're using very simple algorithm to determine the 3 things which we need. Oh, and this is wrong. I don't understand why is this working. It should not. Okay, anyway. So what we've done is we took a width by just taking the amount of characters until we hit the first new line. This is our width, and we just take its length, right? Our height is just the amount of new lines we have plus 1 extra row. Our data is absolutely everything that just isn't a new line, and then because we return absolutely any type of tiles, we also need to pass in this little function that this function that takes a character and creates this tile data. And in the end, we just compose these functions together, and we obviously pass in the string, this string loaded. The reason why I'm saying this doesn't work is because there is no name here, and I want to pass a path to a file as the name of this tilemap. But for some reason this compiled and it just worked, and that's a bit crazy. Say what? So I guess I'm gonna be fixing the code now and see. String to map. No, tilemap, this is the name. Okay, I'm very confused with this, and I don't understand why it works. But actually, I wanted to just say one thing. When we created, before I fix this, when we created this function, this is how it looked originally, right? So you don't really know what these 2 values are. You know, you don't understand from just looking at declaration what is the index and what is the width. So I decided to add some type aliases just to make sure that whenever somebody reads the code, they have a quick understanding of what data goes into each place. Now, the type aliases, they won't help with crashing the compiler if you pass in a wrong type, right? But it's not really important. The important part is that when somebody reads this declaration, they're gonna be like, oh, what is the width type? And they're gonna search in a repo and just say, oh, okay, I can pass any int type. But they already learned that the second parameter is width, not the first. Okay? So, okay, let's fix this. Let's do that. I'm gonna do the reverse of ETA reduce just to discover where my error is. And since we're only 15 minutes in, because I just explained what I've done, I guess we could add some code in the end. Okay. Okay. Okay, let's go here. I don't understand, this should be the same. Okay. So we're gonna name the tile map. And now we can need to reduce back. There you go. That's a really interesting error. What happened before is that it's just a sheer coincidence that the name is our first field in the tile map data, and it's a string. So the name of the map became the actual data of the map. I mean, like a raw data. And that's a terrible little bug to have sneak in, but probably it would be discovered soon. Let's see if this works. Perfect. Okay, so as I said, because we're only 18 minutes in, I'm gonna use the time, and in this video I'm gonna try to add together some simple collision detection. And this is going to happen gonna happen here. If you recall, I'm gonna show it once again. When we load our tile map, we require a function that takes just raw map data, a character, and creates a data of type A, whatever type A might be. So we're gonna first create our data, a very simple one that's just gonna be collidable or not. So let's go with let's call it map tile, or just a tile. So it's gonna be floor or a wall. You know what, let's do doors too. Door, and we shall use opened gonna add a type alias for opened. Cool. All right. We're gonna derive show. And now we need a function. We take a character and return a tile instance. Okay, so what are all the character types we have in our map? There's plenty. And this is a wall, obviously. Okay, these are all the double walls. Are they? No, there are junctions too. Like here. And then here. So we have top, no, we have left, top, right, and bottom junction. Okay, so these should be all the double walls. Now let's do the single ones. Corners, wherever we have them. It would probably be a smart idea to just enter all the corners just in case. And this one, right? No, I have that one. Okay, let's just quickly. Come on, turn it on. There you go. And we're gonna want for it single mode. There you go. This one. And there you go. Junctions. Left, right. Top. We have no bottom junctions, so I'm just gonna draw it. I think that's it. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. That's it. 1, 2 for 2 walls. 1, 2, 3, 4. 1, 2, 3, 4. Perfect. Walls are covered. Let's do the floor. and the doors. Door that's closed. We're gonna show the door that's opened with this character. There you go. See, the issue now is that when we start rendering, we're not gonna keep, we're gonna have only this data. We're gonna have only the wall. And then we're not going to know, unless we do some really smart rendering, like checking your neighbors to figure out if it's a junction or anything, we're not gonna know which exactly character to draw. So we're gonna do a little trick. We're gonna store a character instance with every tile so that we can draw it. And, or actually, let's not make it a character instance, let's make it any instance, something that can be presentable. So, here we can just carry any extra data and whatever presentable thing is. So we're gonna have tile character. I'm doing this, you use this when you want to create a binding to a name, and you also want to pattern match. So the reason why is because I don't want to copy characters over, it creates potential for bugs. This way you can immediately see, okay. So character, and then the doors. I guess the floor and the doors would be the only one that we do not care about their representations, but you know, who knows, maybe somewhere down the line somebody's gonna want to use a different character to represent the doors and still want to use the same underlying code. Okay. So right here, we're gonna do tile from character, and we're gonna get a tile map full of character tiles. Tile map full of tiles on cars. So when we draw the glyph is not just gonna be a character. It's also going to be a type. So we can pattern match here, or we can just extract. How do we do this? Just a function should be enough. Presentable, drawable. It's kind of a stupid name because we do not guarantee it's going to be drawable at all. You know, it could be anything. That's the part I'm not really happy about, but you know what, let's just leave it for now. Regarding the doors, we don't care about what this is. There you go. So down here where we render a map, we're just gonna do drawable from tile. And this should build. Nope. Oh, missing brace. Right. Okay, I guess it's in the update. No? Somewhere we made sure to ensure initial game. Ah, there you go. This is the error. Our render assumes that we're gonna get a char, but we won't. We're gonna get a tile of char. See, ideally, I would just create a type class here that's gonna always return a character. And yes, this is true. What if you run into something that has nothing? We're gonna pretend it's a wall, and the character for this wall is gonna be question mark, because we have no idea what it is. Test. Okay. Nice. And now the crown, we're gonna go back to where we moved the avatar, and we're gonna use this map data to figure out if we can move or not. I just want you to spot a pattern here. This. See, it takes an instance and returns instance of exactly the same type, and here too. This means that these things are great candidates to make a state monads, but I'm gonna try to postpone that forward for two reasons. First, I really like pure functions more than I like monadic code, and second, I might not want to create just monad state instance of anything. What I want to create is our own monads using the new type wrapper, and then just using the monad instances to actually implement these monads of ours. I'm gonna show that later when we come to the point where we're gonna start creating domain specific languages for all our data types, obviously when they become more complex, and we start linking these languages to achieve functionality, which is a great way of writing functional code. But for now, let's just focus on simplicity. So new position. This is a new position. So what we need to do is check if we're gonna move there or not. New avatar position. Okay. We need a map. And see right here, we actually do need to interact with the map type. So we're gonna say that we need types of tile, but we don't really care what their representation is. We just want to know what the tile is. So map, game. I don't know why do I keep calling it old game here when it's just a game. Well, I guess because we modify the game, right? Just a little note for the future. That's gonna be much better than what we're doing now, I think. So yes, we want a map, and then we want a data from a certain position. So we're gonna have to create an inverse of this function. So we can call it chord to linear. We'll take vector 2D of chords. Width, and we're going to return a linear coordinate. Plus x. Chord to linear, and the chord is new position, and we get the index. And then we want to fetch from map data, and that's a vector. So I want to figure out if there's a vector function that returns a maybe. This might be too slow. Let's try using this. Accessors. There you go. Safe operator. Okay, and then if this is an invalid coordinate, what are we going to do? Or we should just treat it as a wall. No, I don't like this. Let's do that. Let's do this. We're gonna make sure that we return positions. So we're gonna have, if the things fail, we're gonna keep our position, and if the things are okay, we're gonna return the. Okay, so we can use from maybe. There you go. And then this is map chord, map tile, and then case of map tile some pattern matching here. We don't care what these are. We do care whether the doors are opened and closed. All right. Simple. So if it's a floor, we can return a new position simply because we can walk there. If it's not, then we have to return old position. And you know what? We could probably extract this into the old position. And where do we use the old avatar? Okay. No, sure. So we can do this. Avatar. G. Old position. Old position. Old position. There. That's not too bad. And if you run into a door, we're gonna check if the doors are opened. If they are, we're gonna return new position. If not, they're also bool false in case of true, and check on T. Bool is not visible unless we add data bool and bool function. Some other crashes. What's the problem? Ah, yes. You know what? Let's make sure we do not make a mess. File D. I'm just going to remove the concrete implementations here because we really do not care about them. And the benefit is that we can remove the character and item empty data, and we can just fill the character with there you go. Our characters are gonna be just names for now. I think he's complaining that this isn't a visible function. Yeah. Okay. Cool linear. Oh, all right. Wait, what did I do here? This looks terribly wrong. First of all, this needs a map width. And it also needs a coordinate, but not of new position. Maybe like this. Yeah, from the vector. Okay, yeah. From the vector, pick a linear coordinate that lies at this chord with this width. Sure. No? Okay, so it's not word, it's int. And this expression is growing too big for my Should I accept int vectors? Yes. The answer is actually no, but I just want to make this work because we're running out of time, and then we're gonna fix it next time. Does not type match word actual type hints. Okay, so from integral and then the whole expression. But because we're accepting int, we must make sure that we take the larger between this and 0, and then otherwise if we convert to word and we're in negative, we're gonna wrap back into like billions. Okay, and here obviously we have to return the pure because we are inside the maybe monad. So I'm pretty sure this is gonna work, and now when we run we're probably gonna be in the wall. There you go. I'm trying to move out and I can't, and it doesn't work. So the one test I'm gonna do, because we have no way to interact with our objects right now, I'm gonna change this to the open door character, and we should be able to walk out of it. That new make was not necessary, but whatever. Okay, there you go. So we have basic collision detection and pretty good thing going on here. Well, in hope that this video does not have glitches now when I stop recording, I'll see you next time in part 4.